My name is Michal Nowak. I'm from Krakow, Poland. I work at Academic Center for Materials and Nanotechnology at the AGH University of Science and Technology. And within this short talk, I wanted to present you our work where we considered how Andreev reflection in approximatized nanostructure affects Aronov bomb oscillation period in a quantum interferometer. Let me first briefly introduce the concept of induced superconductivity. Let us imagine that we have a normal system that could be a wire or two-dimensional electron gas in anyhow, this is a semiconductor. And when part of this semiconductor is covered by the superconductor, the Andreev reflection between the normal part and the superconducting part opens induced gap, which here I call delta, in the semiconductor, which is of course smaller than the gap of the superconductor itself. And now if we consider an electron incoming to that sandwich, of course it cannot infinitely long propagate in the approximatized part. It will be Andreev reflected. However, it will propagate along certain length in this proximatized region, and this length is called quasi-particle coherence length. So here we see a probability density of such quasi-particle, and we see that in the proximatized part it has this evanescent tail, which can be approximated by such expression, and psi is the quasi-particle coherence length. So this is very similar as superconducting coherence length that determines, again, how deep into the superconductors the quasi-particle can enter before being Andreev reflected. And again, similarly to superconductors, this quasi-particle coherence length is determined by the Fermi velocity of the quasi-particles and the size of the induced gap as shown here. Those sandwiches, those superconductor semiconductor hybrids are very important because by using them we can create an effective material which inherits the spin properties of the semiconductor, so strong spin orbit coupling, Zeeman effect, with the electron pairing from the superconductor, and in turn create, for example, an effective P-wave superconductor and observe Majorana bound states, which were first observed in 2012, at least signatures of them, and they are still under debate if they indeed exist in these heterostructures. But I won't be speaking about topological superconductivity in my talk. Rather, I want to focus on this simple phenomenon of quasi-particles entering the proximatized part. So, for example, if we have an NS junction like shown here, where two-dimensional electron gas in indium arsenide is partially covered by a superconductor, and then the quasi-particle from the normal part would enter the proximatized part, but at certain distance before being Andreev reflected. Why this is important? Well, for example, let us imagine a device as shown here. So we have a nanowire which is partially covered by a superconductor, and the ratio between the quasi-particle coherence length and the mean free path in the system determines how the transport occurs in this device. For example, if the coherence length is shorter than mean free path, the device is ballistic, and this is an important feature of such structure. So it is crucial to know the quasi-particle coherence length in those devices. And I want to speak about Aronov bomb effect in quantum interferometers. So we all know how Aronov bomb effect works. An electron beam or just one electron wave function is split into two paths, and in external perpendicular magnetic field, the vector potential, the integrated vector potential along these two paths gives us two different phase shifts, and when the beams meet, dependingly what's the phase difference, we'll observe destructive or constructive interference. And this leads to Aronoff-Bohm oscillations as observed in, for example, quantum rings, when where a metallic ring is put into external magnetic field, and then we observe conductance oscillations as the magnetic field is increased. So I want to speak about quantum rings proximatized by superconductor, which nowadays can be realized experimentally. So, for example, like here we have this semiconductor ring proximatized or connected to two superconducting leads, or one can use crossing nanowires that form this hashtag structure, and when this hashtag is connected to two normal electrodes, Aronoff-Bohm oscillations are observed. So it is possible to contact these interferometers with superconductors, and this is exactly the system that we'll explore theoretically. So we consider a quantum ring, which is partially covered by a superconductor. So in our calculation, we just consider two regions, one without the superconducting pairing and one with the superconducting pairing, and the ring is connected to two leads. One is normal one and the other is superconducting. We use Bogly-Bov-de description of the system. We include spin-orbit coupling, and of course we include orbital effects of the magnetic field by the canonical momentum with the vector potential in the with such a gauge. And then we use pair substitution of the hopping elements, and finally calculate the conductance of the system, which basically is obtained by tracing how electrons reflect into the left lead and how holes after Andreev reflection reflect to the same lead. So the main idea that we have is as follows. Let us imagine that we have a normal ring. So electrons enter from the left, they go to these two upper and bottom paths, and they meet here, and here the interference occurs, and of course the conductance would be dependent on the magnetic field. Each time the magnetic flux is enclosed in the ring, we will see conductance drop, for example. But now, if we imagine that half of the ring is covered by the superconductor, now what would happen is that the electrons would enter the NS junction and then propagate along the distance psi, after which there would be Andreev reflected and the hole would retrace the same paths as electron. And only here the holes would interfere with each other. So now we see that actually the vector potential or the phase due to vector potential would be accumulated on a path that depends on the length of the normal part and the quasi-particle coherence length. And indeed, if we look at the local density of states calculated, we see that the quasi-particles propagate in the normal part and then form evanescent waves in the proximatized part. And if we look at the conductance of this structure, first forgetting about the superconductivity, independently of the energy of the injected quasi-particles, we observe Aronoff-Bohm oscillations of the conductance. But now, if we include the superconductivity, for the quasi-particles with energies larger than the superconducting gap, we see that not much is changed. Well, we see some resonances, but that's not the important thing. The period, anyhow, is preserved. But if we decrease the energies of the quasi-particle below the superconducting gap, we see, firstly, that the conductance is amplified, which is easy to understand because now we inject two electrons, one electron enters and the hole goes back, which means that we transfer two electrons into the superconductor. That doubles the conductance. But we also see that the Aronoff-Bohm period is now decreased as compared to the situation without superconductivity. So indeed, it seems that there is some extra length along which the phase is accumulated. Now, if we look at the conductance versus the magnetic field for varied magnitude of the induced gap, we see that as the induced gap decreases, the Aronoff-Bohm period also decreases. And this is actually something that we would expect, because Decreasing the superconducting or the induced gap increases the coherence length, and by that increases the length along which the phase is accumulated, and by that decreases the Aronoff-Bohm oscillation period. Now, if we know the geometric properties of our device, we can actually integrate the path along which the phase is accumulated, and from that calculate the Aronoff-Bohm oscillation period in magnetic field. But knowing this period, we can actually recalculate it into the coherence length. And this is, in our opinion, very useful, because now doing such an experiment would allow to extract the coherence length from the geometric properties of the device and the measured Aronoff-Bohm oscillation period. So in this plot, we show the extracted coherence length with the red dots and compare it to the coherence length which numerically can be extracted directly from the band structure or the dispersion relation of the proximatized part. And we see quite nice agreement. Indeed, when the gap is decreased, the coherence length becomes larger. And finally, we checked how robust is this effect. So, for example, with regards to the size of the proximatized part, so we see that as this part becomes smaller, the induced, the calculated coherence length is almost constant. Only when the size of this part becomes comparable to the coherence length itself, we see that, well, the extraction here breaks. And also, we checked, in these devices, which are made by, for example, proximatizing semiconducting nanowires with superconducting shell, the electronic properties of the nanowire itself can change due to the metallic shell that surrounds it. So, for example, we checked how our results would differ if we assume that there is, for example, a chemical potential mismatch between the normal part and the one proximatized by superconductor, or what happens if the spin-orbit coupling constant varies between these two regions. And in all those cases, we see that actually not much changes, and we can still very well extract the coherence length. So, to summarize, I showed that in an NS junction, the quasi-particles propagate in the proximatized region on a distance of coherence length. In partially proximatized ring, the phase accumulated by electrons and holes is extended by the coherence length, and the extra phase accumulated decreases the Aronoff-Bohm oscillation period. And finally, knowing the geometry of the device, it is possible to extract the coherence length from a magnetotransport measurement. So with that, I would like to thank you for your attention.
More questions? Do you? You do? Christina, do you see questions?
No, there are no questions on the
chat. Okay, maybe then I have a naive question. So it looks like using your device and experiment, and your calculations, one can use this kind of experiment for independent measurements of the coherence lengths, right?
Right.
And okay, can you sort of indicate what else, for what else your device can be used? Just like some ideas.
Well, that was our proposal for a nice experiment that I think is within a reach of current technology, because actually those hashtags or rings are being studied in labs. But I think the step further, step beyond that, would be actually to use these devices to probe the topological superconductivity. So, for example, what would happen if you indeed proximatize half of the ring or part of the ring, and also include the magnetic field maybe in plane strong enough to close the trivial gap and open topological gap, and then maybe observe how the Aronoff-Bohm oscillation period is changed when Majorana bound states appear at the edges of the proximatized part. So I think that would be a nice exploitation of these devices.
Very good. Well, thank you so much again.
Thank you.
Now probably, okay, we have our coffee break, and I think that we start the continue the session just according to the timetable, right?
Thank you again.